Stretching across the Peruvian mountains from Cusco through Ollantaytambo to Sacsayhuaman lies a collection of stone constructions that defy conventional understanding. These aren't ordinary ancient barriers with standard mortar joints and uniform blocks arranged in predictable patterns. Instead, they present geological enigmas where enormous stones reaching 200 tons interconnect with extraordinary accuracy, achieving tolerances of half a millimeter where not even a thin blade can penetrate the gaps. Each stone possesses completely unique geometry with numerous angles and flowing curves. For generations, scholars assigned these constructions to the Inca civilization, placing their creation between approximately 1400 and 1530 CE. The standard interpretation seemed straightforward. The Inca were exceptional stonemasons who methodically shaped these massive blocks through persistent pecking and grinding with harder stone implements.
Yet there's a crucial detail rarely discussed. These constructions possess flexibility. This isn't symbolic language, but literal mechanical behavior. Peru encounters substantial seismic activity on a regular basis. During these tremors, the ancient barriers actually move. Individual stones shift marginally, absorbing kinetic energy before returning to their original configuration. Meanwhile, Spanish colonial structures built directly atop or beside these walls collapse into fragments. This represents documented, verifiable engineering that contemporary seismologists have examined and cannot completely reproduce. The Peruvian constructions aren't merely precisely assembled, they function as adaptive systems that have endured 5 centuries of seismic events that demolished everything constructed subsequently. The fundamental question extends beyond how they carved the stones. It encompasses how they created an earthquake-resistant mechanism centuries before formal seismology existed, using construction approaches that appear to contradict basic principles governing how stone structures should function. To grasp what makes these barriers so remarkable, consider the most celebrated examples in Cusco's historic district, particularly along Hatton Mioc Street, where a single famous stone displays 12 distinct angles fitting flawlessly against surrounding blocks. However, the genuine mystery lies at locations like Sacsayhuaman, where zigzagging barriers feature stones weighing between 90 and 200 tons, carved into elaborate polygonal configurations with anywhere from 6 to over 30 contact points with neighboring stones. These aren't rectangular blocks. Each stone is distinctive, irregular, and asymmetric, with curved surfaces, protruding sections, recessed areas, and angles that appear almost organic in nature. Yet they interconnect with such exactitude that engineers employing laser measurement instruments in 2011 discovered gaps averaging under half a millimeter between stones. Half a millimeter between stones weighing equivalent to a commercial jetliner. What undermines traditional explanations is that the contact surfaces aren't flat, they're three-dimensional interlocking puzzles. A single stone might possess 15 different faces, contacting 15 different stones, each face at a distinct angle, each curve matching the corresponding curve on its neighbor with perfection. Contemporary stonemasons who've examined these constructions describe the precision as exceeding practical necessity. If stability alone were the objective, you could achieve that with considerably less exactitude. The level of precision discovered in these Peruvian barriers serves a purpose beyond simple stability, and that purpose appears to be mechanical flexibility. Dr. Pratzen, an architectural historian at UC Berkeley, dedicated years to studying Inca stonework and performed experiments attempting to duplicate their methods. His team successfully demonstrated that hard river stones could shape softer limestone through patient pecking and grinding. However, Pratzen himself recognized a significant problem. His experimental blocks required weeks to shape and fit, achieving nowhere near the precision of the originals. More critically, his blocks were simple rectangular forms with flat surfaces. When attempting to replicate the complex polygonal fitting found at sites like Sacsayhuaman, the time required increased exponentially. His assessment was stark. The Inca could have technically accomplished it, but the time investment would have been nearly incomprehensible. For a single barrier at Sacsayhuaman, using his experimental rates, construction would have demanded thousands of workers laboring continuously for decades, and that assumes they achieved success on the first attempt. Here's what makes this even more perplexing. You cannot test-fit stones of this magnitude. Consider the logistics. You're working with a 100-ton block. You shape one face to fit against a neighboring stone. You somehow elevate that 100-ton block into position to test the fit. It doesn't fit perfectly. There's a gap, or the angle is incorrect by a fraction of a degree. So you lower the 100-ton block, reshape the surface, and lift it again, and again, and again. Modern engineers would employ computer modeling and precision measurement instruments to calculate exact angles before cutting. The Inca supposedly accomplished this by visual assessment and trial and error, with stones weighing as much as commercial aircraft. The mathematics doesn't support this, the timeline doesn't support this, and the precision is unnecessary unless it serves a specific engineering purpose beyond what scholars have traditionally acknowledged. In 1950, a major earthquake struck Cusco, measuring 8.1 on the Richter scale. Spanish colonial churches collapsed, modern buildings cracked and disintegrated. The cathedral required extensive repairs, but the ancient Inca barriers stood firm, not just standing, but completely unchanged. The polygonal constructions showed no new cracks, no displacement, no damage whatsoever. This occurred again in 1986, another significant earthquake struck. More colonial buildings sustained damage. The Inca barriers remained perfect. Seismologists began paying serious attention. Studies performed by the Pontifical Catholic University of Peru in 2005 revealed something extraordinary. During seismic activity, the Inca barriers don't resist the energy like modern structures. They absorb it. The stones actually move. Laser monitoring equipment detected that during tremors, individual stones shift slightly, just millimeters, relative to their neighbors. The entire barrier performs what engineers call dancing, a coordinated micro-movement where stones lift, shift, and resettle as the seismic waves pass through. This shouldn't be possible with dry stone construction. Conventional engineering wisdom dictates that stone barriers without mortar are inherently unstable during earthquakes. The stones should separate and the barrier should collapse. That's exactly what happens to dry stone barriers built using European techniques. But the Peruvian polygonal barriers don't behave according to conventional engineering principles. The complex, irregular shapes of the stones, with their multiple contact points at various angles, create a mechanical interlocking system that actually becomes more stable when subjected to multi-directional stress. Think of it like three-dimensional puzzle pieces that can move slightly but cannot separate because every direction of potential movement is blocked by a protruding section or recessed area on a neighboring stone. The more complex the shape, the more secure the interlock. Modern seismic engineering has developed similar principles: base isolation systems, flexible joints, and energy dissipation mechanisms. But engineers developed these in the late 20th century after studying earthquake physics. The Peruvian barriers demonstrate these principles, built into stone construction from at least the 1400s, possibly much earlier. This has led some researchers to propose what's called the pre-Inca hypothesis, that the most sophisticated polygonal barriers significantly predate the Inca Empire and were built by an earlier, unknown culture with advanced stonework knowledge. The Inca inherited these structures, reused them, built upon them, but didn't possess the original knowledge to replicate the precision. Dr. Arthur Poznański, a Polish-Austrian engineer who studied Andean archaeology in the early 1900s,
argued that the stonework showed signs of being much older than the Inca period, possibly thousands of years older. His dating methods were controversial and largely dismissed by mainstream archaeology, but his observations about construction quality differences have never been satisfactorily explained. Modern analysis has added new complications to this mystery. In 2014, researchers using 3D scanning technology to map the stone surfaces at Ollantaytambo made a strange discovery. The tool marks on many of the most precisely fitted stones don't match the tool marks on stones that are definitively known to be Inca work. The Inca used a pecking and grinding technique that leaves characteristic dimpled patterns on stone surfaces. But many of the polygonal stones showed different patterns, smooth, flowing tool marks suggesting different techniques or different tools altogether. More strangely, some stones show evidence of being cut with straight, precise lines. That should be impossible with stone tools. A few researchers have controversially suggested the marks indicate diamond-tipped or other advanced cutting tools, though this claim is heavily disputed. What's not disputed is that the tool marks don't consistently match across different construction phases, suggesting either that techniques change dramatically over time or that different groups with different technologies worked on these sites. Then there's the transportation mystery, which becomes even more baffling when you understand the flex system. The stone quarries for Sacsayhuaman are located over 20 kilometers away across rough terrain, including at least one river valley. The largest stones weigh 200 tons. The Inca had no wheeled vehicles, no draft animals large enough to move such loads, and no metal tools strong enough to work the hardest stones. The conventional explanation involves massive teams of workers using wooden rollers, ropes, and ramps. Experimental archaeology has shown this is theoretically possible, though extremely difficult and time-consuming. But here's the new problem the flex system introduces. The stones aren't just heavy, they're precision crafted. You cannot shape a stone after you've moved it into position on a barrier without risking damage to already placed stones. The complex polygonal shapes with their multiple contact points at various angles mean each stone must be custom fitted to its specific location. This requires shaping the stone to exact specifications before moving it. In other words, the stones are pre-shaped. So you're not just transporting a 200-ton block, you're transporting a 200-ton block that has been pre-shaped with dozens of precise angles and curves. Which means any damage during transport, chips, cracks, surface abrasions, ruins the precision fitting. Modern heavy-load transport companies protect valuable cargo with extensive padding, shock absorption systems, and careful handling protocols. How did ancient workers move 200-ton, pre-finished precision stones across 20 kilometers of rough terrain without damaging the carefully shaped surfaces? Nobody has a satisfactory answer. Some researchers have proposed that the stones were shaped on site, not at the quarry. But this creates its own impossibility. Where are the enormous quantities of stone chips and debris that would result from shaping hundreds of massive blocks? The stone waste should be everywhere, yet excavations around these sites find relatively little. There's also the sequence problem. To create the interlocking flex system, stones must be placed in a specific order, with each stone shaped to fit against stones already in place. This means you cannot prefabricate all the blocks and then assemble them. You must place and fit each stone sequentially, one at a time. This makes the construction timeline even more implausible. If each 200-ton stone requires weeks or months to quarry, transport, shape, test fit, adjust, and finally place, and you need to do this hundreds of times in sequence, you're looking at construction periods spanning multiple generations. Yet the historical record suggests these structures appeared relatively quickly, within a few decades of concentrated building activity during the height of the Inca Empire, except that quality differences suggest the most impressive work might be much older. In 2019, a team of civil engineers from Japan's Seismic Research Institute conducted a detailed analysis of the Sacsayhuaman barriers using laser scanning and computer modeling. They created digital models of the stone arrangements and ran seismic simulations. Their conclusion was startling. The polygonal interlocking pattern is mathematically optimized for seismic resistance. The specific shapes, angles, and contact points create a network of forces that distribute seismic energy across the entire barrier structure, rather than concentrating stress at any single point. This is sophisticated structural engineering. Modern earthquake-resistant buildings use similar principles: load distribution, flexible joints, and redundant pathways for force dissipation. Engineers developed these concepts using computer analysis, physics calculations, and lessons learned from catastrophic building failures. The Peruvian barriers demonstrate these principles in stone construction from at least 500 years ago, possibly much longer. Either the builders possessed theoretical knowledge of structural dynamics and seismology that wouldn't be formally understood until the 20th century, or they refined their techniques through centuries of trial and error, and that would require a much longer construction tradition than the conventional timeline allows. The Japanese researchers stopped short of claiming impossibility, but they explicitly stated that replicating these barriers using period-appropriate tools and methods while achieving the same seismic performance would be extremely challenging, even for modern engineers with computational tools. Recent discoveries have added another layer to the mystery. In 2021, ground-penetrating radar surveys at several sites in the Sacred Valley revealed what appear to be older structures beneath the visible barriers, possible foundations or earlier construction phases that predate the currently accepted dating. These findings are preliminary and controversial, but they support the hypothesis that the most sophisticated stonework might be significantly older than the Inca Empire, with the visible structures representing only the latest phase of a much longer construction tradition. If true, this would explain the knowledge gap. The impressive polygonal barriers aren't Inca innovations, but inherited structures from an earlier culture with advanced stonework techniques. The Inca reused and built upon these structures, but gradually lost the original knowledge, resulting in the declining quality visible in later editions. This hypothesis is speculative, yet it addresses several persistent problems: timeline implausibility, toolmark inconsistencies, the quality decline, and Spanish accounts of Inca workers being amazed by their own ancestors' alleged achievements. Some alternative researchers push this further, proposing that the stonework dates back thousands of years to a lost civilization with technology comparable or exceeding our own. This enters the realm of fringe theory and lacks hard evidence, but the legitimate questions about dating techniques and knowledge transmission keep the debate alive. What we know for certain is this: the Peruvian polygonal barriers represent a level of stonework precision and structural engineering sophistication that challenges our understanding of ancient capabilities. The flex system isn't myth or exaggeration. It's observable, measurable, and functioning exactly as designed after centuries of seismic testing. Modern engineers acknowledge they would struggle to replicate this work using equivalent tools and methods. The timeline for construction seems implausibly short. The tools available seem inadequate for the precision achieved. The knowledge required seems anachronistic for the period. Yet the barriers exist. They work. They've survived earthquakes that destroyed everything built afterward. The conventional explanation, patient Inca craftsmen using stone tools to slowly and precisely shape blocks through trial and error, isn't wrong exactly. It's incomplete. It explains the how in theoretical terms, but doesn't adequately address the time, precision, and knowledge questions. Alternative explanations, earlier cultures, and other more controversial theories fill the gaps, but lack definitive proof. What we're left with is a construction method that shouldn't work as well as it does, built with tools that shouldn't achieve such precision. using engineering principles that shouldn't be possible without formal structural theory, and completed in a time frame that shouldn't allow for the required experimentation and refinement. The Peruvian barriers aren't just impressive ancient architecture, they're a challenge to our assumptions about technological progress and knowledge transmission. The flex system is real, documented, and still not fully explained. These barriers have stood for at least 500 years, possibly much longer. They've survived earthquakes that flattened modern buildings. They've endured without mortar, without metal reinforcement, and without the techniques we consider essential for durable stone construction. And after more than a century of archaeological investigation, we still cannot definitively answer the most basic question: how do they actually do it?
The stones themselves keep their secrets. They flex, they dance, they absorb seismic energy with elegant efficiency, and they remind us that ancient peoples achieved things we still struggle to understand, let alone replicate. The Peruvian barrier method has been partially exposed through modern engineering analysis. We understand the flex system now, how it works, why it's effective, and what principles make it successful. But understanding the result isn't the same as explaining the process. Until we can answer how these barriers were actually constructed with the precision required for the flex system to function, using the tools supposedly available and in the time apparently required, the Peruvian polygonal barriers remain one of archaeology's most compelling unsolved mysteries. They're hiding in plain sight on the streets of Cusco and the terraces of Sacsayhuaman, flexing with every earthquake and outlasting everything we build.